Hi, I'm Felippe Roza and I'll present the work done together with Maximilian Henne, Karsten Roscher, and Stephan Günnemann called Assessing Box Merging Strategies and Uncertainty Estimation in Multimodel Object Detection. The problem consists in an ensemble of object detectors trained independently. Each model outputs a list of detected bounding boxes, respective labels, and confidence scores. The merging strategy is the method responsible for combining the different predictions in order to get the final detections. When combining different bounding boxes, it is possible to get also uncertainty estimates for each coordinate variance, represented in the output vector. This same framework can be applied to different sampling-based methods, such as Monte Carlo dropout. In this work, we consider two different approaches to find uncertainty estimates regarding the variance of the bounding box coordinates. The first method follows the framework shown in the previous slide and consists in calculating a covariance matrix from the bounding boxes obtained from the different models. This approach will be referred to as ensemble variance. Another way to achieve uncertainty estimation is by allowing the individual models to output its own spatial variances. We integrated KL variance and variance voting into our vanilla YOLO and efficient DAT models. Both methods were proposed by Henne et al. The final box uncertainty is then computed by averaging the variances for each coordinate. These will be referred to as KL var ensembles. Here, the KL var approach is presented. It is similar to the framework previously shown, but as you can see, the models are predicting variance values for each coordinate alongside the bounding box prediction. We move now to the box merging part. The first important thing is how to group the detections that correspond to the same object. It is done by choosing bounding boxes with intersection over union above a given threshold, in a similar way to what is done in non-maximum suppression methods. But instead of suppressing the overlapping objects, we keep the clusters for the next step. Such clusters are supposed to represent the predictions from different models on the same object. Now, I'll present the different methods compared for merging the boxes, that basically tells how to combine the clustered boxes. The first is the max method, which consists in choosing the box with higher confidence score from the ensemble. If the softmax confidence is well calibrated, which is usually not true, it should select the bounding box that overlaps better with the true object. The next methods are based on averaging the boxes in a cluster. The first and simpler one consists in calculating the coordinate means. Next, we have weighted box fusion, proposed by Soloviev et al. The final box is given by the weighted average, where the weights are the normalized confidence scores from each prediction. Since we also have variance estimation from our KL variance models, we modify the weighted box fusion method by replacing the weights with the mean variances, calling it variance-weighted box fusion. Lastly, the variance voting method mentioned before was adapted to choose the boxes based on the variance estimates. Now, with the results. The experiments were made with YOLO and efficient DAT, consisting in 7 models for each ensemble. The models were trained in the KITTI dataset without any specific tuning in the hyperparameters, since the goal is to compare the different methods and not improve the state-of-the-art performance. Since some of the box merging methods rely on the confidence scores and others on the variance estimations, we wanted to test which is a better quality indicative for the box predictions. To do so, the following plots were made. The y-axis represents the intersection over union between the prediction and corresponding ground truth. The x-axis is the confidence for the plots A and C, and sum of variances on B and D. Although C shows a subtle correlation for the confidences, in A we see that apart from the higher concentration of detections on the top right corner, a somehow uniform distribution appears on the rest of the predictions, indicating that only the higher values are really meaningful. For the variances, the scatter plot shows the predictions better distributed along the fitted line, and the histogram also shows a higher correlation. The conclusion is that the variances seem to represent better the spatial quality of the predictions. Now, I'll present the results for all the methods described before for the efficient data ensembles. The YOLO results are also in the paper, but the behavior is similar and will not be presented here. In the table are the MAP, intersection over union, and PDQ scores without any uncertainty estimation. For the PDQ, 0 variance matrices were provided, as if the model is completely certain about its predictions. What we see is that, although variance voting performs slightly better, all the results are quite similar. The max method is the worst, which may be related to the results shown in the last slide, but it doesn't hold true for the averaging methods, where the weighted box fusion and the variance modification perform virtually the same. Now, uncertainty estimates are provided. Since only PDQ can benefit from it, the other metrics were omitted. We can see that by using the ensemble variances, which means the variances from the boxes in a cluster, the PDQ scores are more than doubled. The KL variance ensembles improve even more on the metric, given the overall better results. To conclude this presentation, different merging strategies were presented. We found out that variance estimation represents better a box correctness than the mostly used softmax confidence scores. However, when comparing merging methods based on the variances, there was no visible improvement over the confidence counterparts. On the other hand, there is still room for improvement in the uncertainty estimation. The KL variance ensemble requires to change the individual models, but proved better when compared to the variances obtained from the clustered bounding boxes. As future work would like to extend these experiments on different datasets. Kitty has in general small objects in particular image dimensions. Comparing with other datasets would allow to check if some bias was added on the box merging results. This work only comprised the bounding box uncertainty, but PDQ also takes the classification uncertainty into consideration. Different methods could be tested to further improve the PDQ scores. And finally, test if combining the ensemble and KL var ensemble variances can improve the PDQ results. Thanks for listening.